Hi, welcome back. We're in lecture 11, and this is segment 3. The topic of the lecture is multiple regression. In this last segment, we're going to look at exactly how the regression coefficients are estimated using matrix algebra. So again, if you're not familiar with matrix algebra, go back to segment 2. It provides a little bit of a refresher. But assuming you've done that or you're already comfortable with matrix algebra, let's go ahead and see how these regression coefficients are estimated. So again, just like regular simple regression, the values of these coefficients are estimated such that the model yields optimal predictions. And again, how do we do that? Well, we just minimize the residuals. So remember, the residuals are just the difference between the actual score on y, or the observed score on y, and the predicted score on y. We get the sums of squares residual by taking all of those deviations and squaring them. So sum of squared residuals gives us sums of squares. We want to minimize that value. That's ordinary least squares estimation. So but how do we do that when we have multiple predictors in the model? We have to solve for multiple regression coefficients at once. Well, we do that through matrix algebra. So to make this a little simpler, I'm going to just do this in standardized form. So what that means is we can take out the regression constant. Assume the regression constant is 0. So the predicted score on y when all x's are 0 is 0. So we can just drop that out of the equation. So we drop that out of the equation, then the regression equation for the predicted score is just b times x. And now think of everything as a matrix. Okay, there's a little bit of a change in perspective if you're not used to matrix algebra, so just wrap your head around that. If this is new to you, everything is a matrix. So the predicted scores are a matrix. They're actually just a vector because we just get one predicted score on each individual. But it's an n by 1 vector. That is, there are n rows for a number of people, and there's just one column because we're only getting one predicted score in multiple regression. The betas, or the regression coefficients, is a k by 1 vector, and k is just the number of predictors. And then x is going to be an n by k matrix with n number of rows times k number of predictors. So here is the formula. What we want to do is solve for b. So that's not that hard, just we have to apply some basic algebra, right? So to solve for b, what I did first was I'm going to replace the predicted scores with the observed scores because we don't know the predicted scores, right? And then I'm going to conform x and b to make them conformable for matrix multiplication. So what I wind up with is this formula, y equals x times b. So I have y equals x times b, but I still need to solve for b. So how am I going to do that? Well, let's make x square and symmetric. And to do that, I'm going to pre-multiply both sides of the equation by the transpose of x, x superscript t. If I pre-multiply x by its transpose, that's going to make it square and symmetric. And remember, anything I do to one side of the equation, I have to do to the other side. So now, if I multiply each side of the equation by the transpose of x, I get this formula here. Now to solve for b, what I want to do is get rid of everything that's on the right-hand side of the equation. So I want to get rid of x transpose x. To get rid of something in basic algebra, you would just divide by that, right? So I would divide by x transpose x. We can't do that in matrix algebra. What we do is we take the inverse and pre-multiply by the inverse. So the inverse of a matrix times itself is an identity matrix, which is essentially like 1. So it's the same as like dividing by and eliminating that term. So if we do that, we multiply each side of the equation by x transpose x to the negative 1. That's the inverse of x transpose x. So I do that on the right side, do that on the left side. As I said, x transpose x pre-multiplied by its own inverse gives us what's called the identity matrix. The identity matrix times another matrix gives you just that matrix. So I times b equals b. So we've succeeded in eliminating everything from the right-hand side of the equation except for what we're solving for, that is the regression coefficients. So now I have a formula I can work with. So here's our solution. We can now solve for b with just x transpose x, the inverse of that, times x transpose y. We know the x values, we know the y values, right? Those are our variables. So that's the formula that we're going to use. That's what R uses to calculate these regression coefficients. So let's use that formula to calculate the regression coefficients from the same data that we used to illustrate matrix algebra. So here was the raw data matrix. And what I'm doing is I'm going to consider this first column y, and then the next one x1, and the next one x2. Because we need one of the variables to be the outcome measure. So again, I'm going to get the row vector of sums. We did this in the last segment. The row vector of means, did that before. Matrix of means, matrix of deviation scores, and finally, this sums of squares and sum of cross products matrix. Now, since I have deviation scores, I can substitute that S sub xx for x transpose x, and S sub xy for x transpose y. So now, the regression equation I can just write in terms of those S matrices. Then, when I do that calculation, I get my regression coefficients. And here are the regression coefficients. There are two of them because I had two x's and one y. One of them is negative 0.19, the other is negative 0.01. To check myself, and if you want to check yourself, if you didn't trust that, I went a little fast there at the end, you could plug that raw data matrix into R, right? And then just run an LM with the first column as the outcome and the next two columns as the two predictors. Run the LM, and you'll see I ran exactly that. I did LM, where the formula was demo. This is just a demo of matrix algebra. So I did demo y as a function of demo x1 and x2. And you'll see we got exactly what we did when we calculated it by hand. So I got a negative 0.188. So I got 0.19. I did a little rounding error when I did it by hand. And a negative 0.008. I got negative 0.01. Again, a little rounding error just by hand. So I just ran it in R to make sure I did it right as I did it by hand. But there you see, if you wanted to, you could do multiple regression by hand. Of course, we're not going to do that because it's so simple just writing in LM y tilde x1 plus x2 plus x3, right? So you'll just do that in R. But now at least once in your life, you've gone through and you've seen how to do it by hand if you had to do it that way.